Today, I had a problem with resistors. I didn't have the right kind. It said assorted resistors, and I didn't have very specifically assorted resistors. That got me thinking about resistors, and so now I'm going to talk about them to build on something I brushed over in an earlier video. Direct from Wikipedia here, resistor is a passive two-terminal electrical component that implements its electrical resistance as a circuit element. All that is saying is that a resistor resists. Now, the current through a resistor is in direct proportion to the voltage across the resistor's terminals. The relationship is represented by Ohm's law, which is I equals V over R, where I is the amperage, V is the voltage, R is the resistance in ohms. Ohms being the generally accepted term when talking about resistance. So here, I've got a pile of resistors. And by the way, given that it's part of Ohm's law, resistors are important. The concepts behind them aren't insanely difficult to understand, but they're important to understand. So, I'm just adjusting the camera here. So, we're going to veer away from Wikipedia. I'm going to show you a few different, two different types of resistors I have here. We've got these axial resistors, which are... to adjust my tripod, I apologize. Okay, we've got axial resistors, which are one of the more common types of resistors. I'm trying to make it so I can see my own screen here. I'm sorry. We've got axial resistors. Undoubtedly the most common type of resistor in hobbyist electronics. Now I say hobbyist because in electronics, you're going to have surface-mounted resistors, which are stuff that I don't delve into because I can't. They're very tiny. So, as you can see, there's a little color code on it, and you've got two leads. It's a beautiful little marvelous piece of technology that is actually pretty simple. That's a small one. Here's a larger one I got off a circuit board. As you can see, it was kind of standing up like this, which is annoying for breadboards. But it's bigger, meaning and you might be wondering, why is it bigger? Well, why is it bigger? Well, as you know, based on the fact that we assign a value to resistance, there's going to be varying values of resistors. However, these resistors are not necessarily this little one is not going to have a larger or smaller resistance than this bigger one. It's not it's not going to necessarily going to have like a smaller resistance than the larger one. In fact, I don't think it does, but I can't really see the code that well on them. I'll get more into that later. So, with the difference between the sizes is the wattage. Resistors, as we know, not everything is invincible in electronics. We've demonstrated that with a fuse. I mean, that's the point of a fuse, not being destructible to prevent overloading. So, resistors can get overloaded, and given the fact that these are ceramic resistors, because ceramic is a natural resistor, and we might as well use it to our advantage. There's also wire windings inside of there, just a lot of wire windings and ceramic stuff to fine-tune the resistance inside these little things. Now, the reason that one's bigger than the other is because only so much wattage can go through before they overload and exceed their capacity of wattage. So they have different wattage ratings. This one, I believe, is just a few standards. Standards of resistors are half watt, quarter watt, sometimes eighth of watt, and 1 watt, which are big resistors. In axial resistors, at least. This one, I believe, is half watt or more. So it can take more wattage. If you've got a higher amperage in your circuit, higher amperage and voltage in your circuit, you want to use a bigger... If you have a higher amperage in your circuit, you want to use a bigger resistor. Those are axial resistors. I've got a lot of them. They tend to come in this little, if you buy them, as opposed to taking them off the circuit board, they tend to come in this little array. And they come in all sorts of different shapes and sizes. And some of them even have words on them. Or ones at least. But that's pretty uncommon. You shouldn't rely on that to back you up if you don't know the codes. and I don't know the code, so I'm not going to say that. When you buy them, they tend to have longer leads, as with most things that you buy, than if you desolder them from a printed circuit board. That's when I desoldered. It works, though. Might as well take it off if I can. So yeah. So we've got axial resistors, and then I don't have very many examples of these, unfortunately, but I've got, and there's these other resistors, I guess you could say. Technically, they are... They're still technically axial resistors, but they have a much higher wattage. This one, right here, may look impressive. May like, oh, that's got a lot of resistance. There's some thermal compound on that. It has a resistance of 2 ohms. It's very low resistance. It's probably just an entire wire in there. There were a couple windings of wire in there. In this little ceramic package, as you can see, and I'll talk more about that burn mark later. But it's only 2 ohms. Not that high of a resistance at all. I don't... to get the center so people can see it. I have it upside down. I'm trying to crane my neck to figure out what I'm looking at. It's not worth it. Never mind. So anyway, yeah, that. And then also, it has a wattage rating on it, just like, but it's printed on here because it's a much bigger surface. Talk about why it's printed on some and not on others. Wattage is 15 watts. It's very high wattage. I got this out of a computer power supply, which it was a 300 watt computer power supply, so as you might guess, it's going to need a decent amount of wattage to get through. Here we've got another one. Okay, it also came from a computer power supply. This one is 1.2 ohms, and it is 5 watts. So, yeah, it's still much higher than these little ones. And for size comparison, that's a normal size one, and that's that. Here's the other bigger one. These are incredibly useful if you're doing experiments involving coils and magnetic field deflections, because they've got a low resistance, but you need some resistance in there, and they've got a very high wattage for you to play with your amperage. So it's useful to have these. They're not as common as these little axial ones, though. But if you take things apart, you'll find them in the power supply of them. So anyway, while we're here, we're going to talk about why there's these little color bands on here. And that's because when resistors were first being implemented in the... let me look at the article. I don't remember what it was, but it was the early 1900s, I believe. There wasn't a big of complicated manufacturing for us to write little letters on, so what's the best solution here? Well, we can just make a few bands of, color on it. And have a little, to figure out what the resistance of the resistor is, you decode the color. So, I'm not going to get the best color here, unfortunately. But I can guarantee you that this one is... Well, it's not a very common one. Let me find a more common one. There's also 4-band and 5-band ones, and you only are going to pay attention to really 3 bands in most applications. Okay, so here's a more common one. Just get it in focus. Okay. I'm just looking at this myself. Okay, so the color code on this one, as you might be able to see, starting from this side, it may not be very clear, but it's brown, black, red, gold. The first 3 are not the one we're going to pay attention to. The shiny one, it's generally going to be shiny on this end, is the one that you don't start with. The one you start with is on this end. So this resistor is a... Well, I'm going to decode it for you right here. Brown is symbolized as 1, and then black symbolizes 0, so we got 1, 0. And then on 4-band resistors, the other band before the last one, second to last band, is the multiplier. So it's essentially the number of zeros we're going to multiply. It's 10 to the whatever that is, but it's just the amount of zeros we're going to add to the end to it, in short. So that one's red. Red symbolizes 2. So we get 10, we add 2 zeros to it, so 10 times 100, and we get, what do we get? We get 1,000. So this is a 1,000 ohm resistor, more commonly known as a 1 kilo ohm resistor. It's only a quarter watt, but that's the decode. The last band is shiny and very reflective gold. That's the tolerance. I need to remember what tolerance means. So, as I was saying, there's a tolerance assigned to these. Tolerance is the variance that could happen or could not happen. It's in a percent, and it's plus or minus. If you really want an exact resistor, which most applications you won't, they tend to be a higher tolerance. Let me just make sure that that's the actual meaning of tolerance, because if I'm wrong, it's going to be kind of embarrassing. Yeah, okay. Higher precision. Yeah, I was right on that. Okay, so tolerance is just the precision of it. 5-band resistors, which are the ones where you have 3 numbers and then your multiplier, then your tolerance, and to be more accurate. Tolerance. The 4-band tend to be less accurate, and in most applications, the accuracy that these are is, I believe, gold is 10%, plus or minus. Even though it may seem specific, it's not going to make that much of a difference. They tend to run as operated, but the worst comes to worst, they are going to go plus or minus 10% away from their marked value. Most of the time, you're not going to even need to notice the tolerance. It's something that you learn to it's something that you learn to ignore. Tolerance almost never matters in hobbyist electronics. That's hobbyist electronics only. There's also a few more kinds of resistors. There's surface-mounted resistors, which I can't show you because I don't have any, because I can't mess with them. They are just like any other surface-mounted component. They're used for integrated. They're kind of like an integrated circuit. There's no leads on them or anything. There's resistors in a line, or a kind of like an integrated circuit of resistors, and those are pretty neat. You've got there's a lot of different kinds of resistors, but those are the most common kinds. Other than that, it's very awkward. There is a common analogy for resistors, and it's nicknamed the hydraulic analogy. Compares electric. I'm going to read from Wikipedia here. The hydraulic analogy compares electric current flowing through circuits to water flowing through pipes. When a pipe is filled with hair, it takes longer it takes a larger pressure to achieve the same flow of water. Pushing electric current through a large resistance is like pushing water through a pipe clogged with hair. It requires a larger voltage drop to drive the same flow. Electric current. This is a very good analogy. Time told. Resistors can also be put in series and parallel. In series is where you take a resistor, and you essentially, what you do is let me just zoom out here. You line them up, hook them up together in a row. This adds the resistance of each individual resistor together. So the resistance total is equal to the resistance 1 plus resistance 2 plus resistance 3, etc., etc., etc. That's in series. In parallel, you take your resistors. This is where the concept of series and parallel comes, by the way. Take your resistors, and I'm gonna just imagine there's wire there. Hook up a wire, and then you so it goes through and out. In this case, what you do is you take 1 divided by the resistor 1 plus 1 divided by resistor 2 plus 1 divided by resistor 3, etc., 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 etc. And your total equals 1 divided by the resistance of all combined in parallel here. 1 divided by. You've got to remember that. If you don't remember that, then your resistance values will be awkward and off. So you have to divide by 1 again to find the answer. So essentially, with multiple resistors in series, you can get more resistance. In parallel, you can get. Where's a diagram too? I need to find that. Just a moment. I'm sorry. Okay, yeah. If you have the resistor by itself, you get 6 volts going across it, and it's a 1 kilo ohm resistor. It's going to come out at 6 volts and at 6 milliamps, assuming that 6 milliamps is what it goes. Never mind. Ignore that. The analogy used is when you put a resistor in series, you're going to get more resistance and less current going through. You put them in parallel, you're going to get less resistance and more current going through. So if you have two 1,000 ohm resistors and you have them in parallel, you're going to have 500 ohms of resistance. And you're going to have twice the current. Twice. It's pretty good. Twice the current. If you had 6 volts going through originally, it goes up to, well, it goes up to, if you have 6 milliamps, it goes up to 12 milliamps. I didn't explain that correctly quite, but it's, you get the idea. Potentiometers are simply variable resistors, and I'll talk about those some other time. And really, in general, it's good to have a lot of resistors. Resistors are pretty cool. They're very useful. Very useful for controlling integrated circuits. As you can see, I've got a lot of resistors, and they're very sharp. Learned that from experience that I would not like that. Anyway, thank you for listening to me ramble on about resistors. Here's a disguised resistor. Sometimes you run into those. I hope you understand them a little bit better now. I still don't understand them completely, but I probably should, but I don't. And I need to go buy more resistors, even though, because believe it or not, it's not enough. Anyway, thank you for watching. I'll catch you later.